Okay, good. Hello everyone. Good evening. Okay. Welcome to the week 2 solving session of linear algebra through geometry. Okay. And my name is Bhavya. I am a PhD in computer science at IIT Madras. Okay. And uh, uh, by the way, since I see a few newer people this week, I just want to make an announcement that my sessions will be happening Tuesdays, okay, 6 p.m. to 8 p.m. And there are, although, two sessions to this course, and one which is held by another TA, Rupesh, and the other which is held by me on Tuesdays. So you are free to choose which one you want to attend because the content by itself will be the same. Okay. By the content I mean the curriculum will be the same. The questions may be different, but it will still be that particular week's content. Okay. And what happens in these problem solving sessions? Well, as the name suggests, we'll be looking at some problems, trying to solve them. If you have any doubts, just ask me, and we can try to work through that doubts. And additionally, what I do is, if there are any questions from the assignments whose deadlines are already due, okay, I'll be discussing some of the more difficult ones from the assignment, or you can tell me which ones to discuss in case I have not discussed the question of your choice from the assignments. Okay. However, it so happens that the previous week's assignment, which is week one's assignment, is not due yet. Okay, which will be due tomorrow. So the assignment will be discussed in the next Tuesday. Okay. Okay. Having said that, let's just begin. So this week's topics are solving system of linear equations. Okay, and there were 4 topics discussed. Okay, of solving linear equations. One is the Gaussian elimination technique, the Gauss-Jordan technique, and using inverse of the matrix, and then finally Cramer's rule. Okay, these are solving linear equations. And previous week we just had a simple introduction of how we can model things into linear equations, okay, and how we can perform these row operations and so on without actually changing the system of linear equations. Okay, and many of these things you may have already seen it. Maybe in, say, if you are doing some undergraduate, then maybe your first year of your undergraduate course, or maybe you've even seen it in high school. Okay, and that's totally fine. But it's not like the entire course is trivial. Bear with the course. Okay, for this week, maybe you'll see a lot of new things in the coming weeks, and in the later weeks, definitely you'll see a lot of interesting and newer things. Okay, now. And the next thing that was discussed in this week is the properties of the inverse of a matrix, okay, and finally the properties of determinant of a matrix. So although this this course relies on interpreting linear equations, linear algebra geometrically, this week's content did not have a lot of geometry involved, but next week onwards it will be very geometry heavy. Okay, so this we are seeing the row view of linear algebra. The row view of linear algebra means that if you have a matrix, then you have these rows in the matrix, okay, and they are interpreted as equations. So the entire matrix represents a system of linear equations, and the column view is that you view them as points, and the columns form what are called vectors. So you'll see the vector view, and vector view is a very nice geometric view of interpreting operations in linear algebra, okay, transformations and so on. And you will very soon see this in the coming weeks. Okay, so now let's begin with the first question. So the question says, solve the following question using substitution, Gaussian elimination, Gauss-Jordan technique. Okay, first thing we want to do is try to solve it using substitution. Okay, these are all different techniques: Gaussian elimination, Gauss-Jordan techniques, Cramer rule, and so on. So let's just directly jump into it. We are supposed to solve this. Okay. Okay, Satinder is here. Okay, hi. Uh, so the first thing we want to do is solve this using substitution. Okay, so you guys must be very familiar with substitution already. Okay, if you don't, then just let me know. Equals z 3x plus 2y minus z equals minus 1. So how do I do substitution? Well, what I simply do is I
multiply equation 2 by 2 and then
multiply equation 2 by
2 by
2.
factor
Okay,
of 2.
great. So multiply equation 2 by 2. Okay, 2 by 2. So what do you get? You get equation 2 is 2x minus 3y minus 2z equals 0. Okay, then
So yeah, but then this will become 2x minus 6y. 6y minus
oh, sorry,
4z.
sorry, yeah, yeah. Oh, what are we doing? 6y minus 4z equals 0. Yeah.
Yes, and then you subtract the equation 1 from it.
No, 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 no. That is, we are going into elimination.
Okay, yes. Okay, that is not substitution. Okay,
Yeah.
all right.
Okay. But yeah, any idea? Instead of elimination, I want to go into substitution, as the name suggests.
So I don't remember what the substitution used to be.
Simplify.
Okay. Yeah, Kishore.
Two equations. Simplifying two equations, getting a value, and then
Yeah,
substituting that
exactly.
value.
Exactly. Good. So it just means that I want to simplify the equation in terms of either x or y or z, and then substitute the value of that particular variable, say x, into another equation, and then get the value of say y, and then continue cascade. Okay. So this multiplying thing is still somewhere between elimination and substitution. We don't really need to multiply here. Okay. So, but we can still do it. It might make things simpler, but for the sake of simplicity, I won't do this. So what I'll simply do is I see this z alone here. I'll bring everything in terms of z. Okay. So from equation 3, I say z is equal to, okay, I bring this z here and minus 1 there, 1 plus 3x plus 2y. Okay, I hope this is clear. Now what do? I substitute this z into one of the two other equations, either one or two. Let's say I substitute z in equation 2. Then what do I get? X minus 3y minus 2, 1 plus 3x plus 2y equals 0. And then what do I get? I get x minus 3y minus 2 minus 6x minus 4y equals 0, and minus 5x minus 7y minus 2 equals 0. Okay, and again I want to do substitution, so either I pick x or y and then bring everything in terms of that. Let's say I pick x. Okay, so I try to bring x equals to something, so I shift 7y there, plus 2 here, and then I do minus 5 here. Okay, so this is what I have. And finally I have this, I substitute the value of x into the first equation. Okay, so 7 substitute x in 1. Okay, then what do I have? Then I have 7y plus 2 minus 5, 2 times this, minus y plus 3z equals 9. Okay, so let's continue simplifying this. Okay, and so let's see, 14y plus 2. Okay, I'll bring the minus sign inside. So minus 14y minus 4 by 5 minus y plus 3z equals 9. Okay. Oh, by the way, I was substituting, what did I substitute? X. Oh, I still have y and z remaining. No? Okay. So what do? I did not substitute one. It's okay. It's okay. I'll just substitute that later. So minus 14y minus 4 minus 5y plus 15z, okay, equals 9 times 5 is 45. So this is what I have. But now I have two variables, right? I need to eliminate one of them. So I do a further substitution. I take oh, I took a massive blood, but it's okay. So let's take into one of the terms, which is I substitute this particular z here. Okay. So I do minus 14y minus 4 minus 5y plus 15z is z is 1 plus 3x plus 4y. 2. 1 plus 3x plus 2y times 15 equals 45. Okay. And then I have minus 14 minus 5y is minus 19y minus 4 plus 15 plus 45x plus 30y equals 45, right? And a lot of terms floating here and there. Okay, but so minus 19y plus 30y is 11y minus 4 plus 15 is 11y plus 11 plus 45x equals 45, right? Now again I have x and y, but I'll substitute again this value, x equals this 7y plus 2, okay, or the I'm bringing everything in terms of y, no? So this means that y equals minus 5x by minus 5x, okay, y equals minus 5x
minus 5x minus 2 divided by
minus 2 divided by 7, right? Minus 5x minus 2 divided by 7, okay. Y equals minus 5x minus 2 divided by 7. Okay, good. So, oh, is it? Oh, it was already in form of x. Okay, so no need to do that. Okay, sorry. What was it? X equals 7y plus 2 minus 5. 7y plus 2 divided by minus 5. Okay, I'll just substitute that here. 11y plus 11 plus 45 times 7y plus 2 by minus 5 equals 45, right? And then I'll cancel this 9, okay. And so what does this make? 11y plus 11 plus 7 nines are 45. Okay, there will be a minus sign. Minus 40. What am I saying? 7 9 63. 63y plus 2 nines 18 equals 45. Okay. So now what do I have? 74y, right? And this is minus 74y minus 29 equals 45. So what does this simplify to?
Slightly incorrect. 11 by minus 63y. So this will become minus 52y.
Where?
While simplifying this, so 11 by plus 11 minus 63y.
Minus
So
63y, yeah.
So it's become minus 52y. So minus 63 plus 11.
Okay, one moment. Minus 63 So this is 7y, and there was a minus below, right? Minus 5.
Uh-huh.
Yeah. So,
There is some simplification. I mean, mistake here. I think.
on which step? This one or this one?
In the last step. So 11y minus 63y is
11
equal to
minus. Okay. I added them. No? I should be subtracting. That's what you mean, no?
yes.
Yeah. Okay. Sorry.
Similarly for the 29 as well.
So this will become 252, right? Minus 52. No?
Yes, and 11 minus 18 minus 7.
So this will be minus 7, right? Okay. Equals 45.
So y is equal to minus 1.
Minus 1, no? Because this will be minus 52y equals 45 minus 7, 45 plus 7, which will become 52, and y equals minus 1. Okay, good. Sorry, I made a lot of mistakes on the way, but okay, finally we got y equals minus 1. And so now the idea of substitution is, now that I've got y equals minus 1, I just keep substituting it here. No, take any of the equations and keep substituting it there, and finally you should be getting some value. Okay, but okay, so you'll be getting, let's see, okay, can you substitute? So you'll be getting actually you don't even need to substitute there, you can just substitute it here, okay, and get the value of x. Okay, so now x equals 7y plus 2 by minus 5. 7y plus 2 by minus 5. Okay. And y equals minus 1. So this means x equals minus 7 plus 2 by minus 5. Okay. Which is minus 9. Oh, no. 7 minus. It's still minus 5 by 5. So it is 1.
Would be plus 1.
No? Yeah, good. And what is z? Now, for z, you can use this equation. Okay, 1 plus 3x plus 2y. 1 plus 3x plus 2y, and you get x equals 1. Then 1 plus 3 minus 2y, because y is minus 1, which is equal to 3 minus 2 is 1. So this is 2. No? So this means the solution is x comma y comma z is equal to 1 minus 1 comma 1 comma 2. Is this correct? No, 1 comma minus 1 comma 2. So this is the solution that satisfies all the three equations. Okay. And what does it mean geometrically? Well, geometrically it means that there are these planes, okay, and they all meet at this particular point. Okay. Now we want to do it using Gaussian elimination, but before that I want to just show it geometrically. So what I've planned is that
I have a query at this point. So these three planes would be intersecting, and the intersection would be a line. So we got the values of x, y, and then g. So what would be the equation of the line then?
No, it won't be a line. That's what I'm going to show you. Okay.
Okay.
So yeah. So what were the three equations? Can you tell me? Okay. So I think, yeah, I have it here. Okay. So the first equation was 2x minus y plus 3z equals 9. Okay. So this is the first plane you have. I'll show it here also. One moment, sorry. Okay, so you have equals 9. Now then you have x minus, so equation 2 is x minus 3y, okay, minus 2z equals 0. Okay, and okay, so you have the second plane, and then you have, I change this color. Okay, yeah. So equation 3 is 3x plus 2y minus z equals minus 1. Okay, great. Okay, how do I change the color? Okay, it's not changing colors. That's bad. Okay, but do you see these 3 points? So while you were asking, right, that they will meet at a line, but we get something better. You see that they meet at this particular point, right? You can see the 3 lines are meeting exactly at this point.
Visualization is not that clear to me.
Yeah, okay. I am not able to color it differently. Can I? Yeah, good. I'll color this red. I'll color this one green. Light green, light green. Okay. Let's say green. Yeah, this one. Okay. Now can you see it?
Yes, I can see, but but still, I mean, so are they intersecting at a point or at a line? Still, I feel that they are intersecting at a line, isn't it?
How is it at a line? See, you can see that they're intersecting at the single point right here. How the see? I can agree
yeah.
that. Can you see my cursor of the mouse?
Yes.
Okay, so you can see that the blue and the green plane, which is the first and the third equation, okay, are intersecting at this line.
Yes.
This I can agree. Next, the blue and the red equations, the blue and the red planes are intersecting at this particular line.
Yes.
And finally, the red and the green are intersecting at this line.
Yes.
And what you can actually see is that, okay, if I see it from this side view, okay, can you see the thin blue line?
Yes.
If I see it from here,
see that probably the intersection of the 3 planes is the intersection of the 3 lines.
Exactly.
I mean, every 2 planes are intersecting over a line, and so what is the geometric meaning of that 2 planes are intersecting over a line? Because they could be.
So exactly. So what does it mean when 2 planes are intersecting over a line? For example, this blue line is intersecting with the red plane, right? This thin blue line represents the intersection of the blue plane and the red plane. This thin blue line.
Yes.
Right. This means that along these points, okay, along these points of x and z, okay, of x's values and z's value, as you can see, look at the axis, okay, x comma z, along these points the red equation and the blue equations agree.
Yes.
Right, that is what it means.
Correct. Yes.
Now if you add this extra axis, if you add this y axis, as you can see here, talking about the depth, okay, no matter, oh okay, actually if you see it brings in the depth also, but even it does not matter from which depth I view it, okay, as you can see I'm zooming in and zooming out along this, what is this axis, y axis, right? I'm zooming in and zooming out. As you see that this thin blue line is still same. So it means that no matter what the value, okay, how do I get the axis back? Oh no. Okay, it means that okay, here it means that no matter what the value of the depth I have, which is no matter what value of y I have, it is same. It does not no matter what value of y I have, it does not matter. They're still intersecting at this particular line. Now, when I add this new line here, new plane here, which is the red plane, okay, the red plane also intersects with the blue plane at this particular line. And what does it mean? It means at these points, okay, at these values of what? Values of y and what is this axis? X. At these values of y and x, the blue equations and the red equations are satisfied. They agree at these points. Simultaneously, these values are able to satisfy accurately the red plane also and the blue plane also. Now, what does it mean when they intersect at this point? They are intersecting at this point, which is the same as the intersection of the red line, okay, and the green line and the blue line. Okay, these three, the intersection of these three lines means that these are the values that is satisfying the red and the blue line, satisfying the blue and the green line, and the green line and the blue line, all three simultaneously. Okay, so, and what is that point? If you plot the value that we actually obtained at the end, which was 1, x equals 1, y equals -1, and z equals 2, it will exactly coincide at that point, as you can see.
Yes. So the intersection of two planes is a line. Intersection of three planes is a point. And what about the intersection of the hyperplanes? Would it be a point or would it be?
That's a good question. Let's say, although I cannot visualize a 4-dimensional plane out here, right? I cannot visualize a 4-dimensional plane out here, but you can imagine that when two 4-dimensional planes intersect, okay, when they intersect with each other, what do you think you will get?
So that would be the intersection of the 4 lines. No, not
no.
because every pair of the planes, but then the plane is there in the 4 dimensions. So if two 4D planes intersect, so what kind of structure that be?
Exactly. So for example, if I have intersection of two planes, will give me what? A line.
A line. But then these two planes are 3D. These two planes are in 3D.
Yeah. They need to be in 3D, right?
Yes.
And intersection of two lines will give me a point. Okay. And okay, you can't go below that. You can't say intersection of 2 points. But what do you think then the intersection of two hyperplanes? And hyperplanes means that, one moment. Okay. Intersection of two 4-dimensional hyperplanes, right? Hyperplanes. What will it give you? By this pattern, it should give you a plane.
A plane, yeah.
Okay.
Oh yes.
Right.
Yes.
Right. It should give you a plane. Now, in the Gilbert-Strang book, there's a nice example given that, in the real world, okay, you could consider the 4th dimension as something else, but it is a popular understanding in physics, in theoretical physics, that the 4th dimension is time, right?
Yes.
So you can consider, but we are made out of planes. Okay, we are made out of several 3D planes. No? And what happens is you have this passage of time, okay, and this, you can imagine the time to be a certain number line, okay, and we are a plane within it, okay, but every passing moment, okay, of every second, say, okay, every second that we see around us, it is an intersection, okay, intersection of a plane on time, okay, with ourselves. Okay, we are the planes, and it is an intersection of a hyperplane, which is a dimension of a time. So you can imagine like there to be like infinite many planes across the line of time, and we are a plane that are intersecting at each of these points within the dimension of time, within each of the planes that represents time. But we are of course three-dimensional creatures, so we are stuck within it. Okay, so and you can imagine like what would happen if you intersect two five-dimensional planes, then you will get a four-dimensional hyperplane. And so
Yes.
what happens if in a system of equations you keep adding new equations? The probability that you will reduce the number of dimensions increases. Okay, and this is an important technique which is used in mathematics a lot. Okay, when you have a n-dimensional system, okay, and you add another n-dimensional system, okay, and you add another n-dimensional equation there, n-dimensional hyperplane there, then you reduce then the probability that you will reduce the dimensions increases. Now, when does it not increase? Okay, when does it not? Is it always true that let's say I remove this line. Okay, let's say I remove this line. Okay, and okay, I'll remove this also for a while. So you have these two planes, right? They are forming a line. Does it mean that whenever I add an equation to it, okay, I add an equation to the system, or in other words, when I add another three-dimensional object here, another plane here, should it always form a point? Should the dimension decrease even more? Does it always need to happen that whenever I add a plane that it will always decrease the dimension?
No, this is not necessary because quite possible that the multiple number of the lines may not intersect. Some of
Exactly.
them, if parallel or what, could be.
Exactly. So let's say there is another line, okay, and which is oh, what equation is this? Oh, what am I doing?
That could be say 4x minus 2y plus 6z. Say.
Exactly. 4x minus
6y
6y
plus
minus 4z
4x minus 4x minus 2y plus 6z. 4x minus 2y plus 6z
minus 2y
plus 6z
plus 6z
6z is equal to say something
is equal to 0, right? Okay.
And this 6z is not necessary. You can make it 16z.
Sorry, 6z is say
instead of
19z. Not 19, 18.
Instead of 6z, you write say 16z.
Oh, sorry, not 18. Sorry, I increase or decrease it 10. Say. Okay. So you can see that these two lines are parallel.
Yes. So I would be interested in seeing that. What if you replace this 6z by 16z?
Okay. If you replace it by 16z, something like this.
Then also, do I get an intersection or not an intersection?
Okay. You may or may not get an intersection. It depends on what is on your right hand side. If it's still consistent, then good. You may or may not get an intersection. It all depends on the consistency of the system, because like if I zoom out, it may so happen that all three of them will intersect at a point, because I can see that all three of them are sort of these two are trying to converge here, and this red plane is also infinite, so it looks like it will intersect. It all depends on what is there on the RHS now, because in the RHS now, if I put something like this, okay, let's say if I put 18, it will not intersect. Oh, it should not be intersecting. That's what I think. Oh, it will intersect. Okay. If I put something like 16z. Okay, that's the thing. Okay, but if I put something, if I put the if I put 6 here, then it will not intersect, because it is basically the same line. If I change this RHS to say 20, it will not intersect, because then I get parallel lines. Or let's make it bigger, let's say 50.
So why did I make it 16? Because by making 16z here, I kept x and y things same. X and y as parallel to the 2x minus y. And say at the time of the intersection, since the z would remain the same, and I would only be seeing the intersection, along the x and the y axis only.
But see, what do you keep on the RHS also matters, no?
So can you do one thing that in the RHS you write 18 here, but still I would like to see that they should be parallel towards the x and the y axis and the z. So are they intersecting? Still are they intersecting, and they should not intersect, I guess.
They should no. It can intersect. It may intersect because it may be that 4x minus 2y plus 6z is 18 and 16z. Nothing is actually stopping it from not intersecting yet.
Yes, I understood. Yeah, fine.
Okay. And but anyway, okay. But to get back to the point that I was trying to make is now you have these 3 points. Okay. Now let's see what happens when you add.
One
Yeah.
question here, Bhavya.
Yeah.
See, of course, see the if two lanes are being pointed on the plane, of course we get a line, but whereas three it comes to a plane, but whereas more than three,
Huh.
it comes to a subspace, right? A subspace on the of the plane
Well,
because
but okay.
four when we draw four equations, right? So we don't even get anytime a point or line. So altogether, what it does is it just divides the space and then makes a subspace. The
Okay,
total
so
space into subspace.
so just to step back, you mean four lines? You are making four
For each
equations, four
right.
equations, and
So when we graph it on the plane, right?
yeah,
These
okay,
four equations.
okay,
So
four
what it
equations.
makes is the subspace. So the total, the four dimensions makes a space, total space.
Yeah.
X, Y, Z, and then some other axis. It makes total space. But when we graph it, when we point these coordinates on the plane to the total space, right? It makes the subspaces.
Well, see, it's it's not entirely correct to call it a subspace because we are still doing the plane view of things. Okay, we when we do it from a column view, I agree. If we are taking each of these as column vectors and then plotting them, then we'll get a subspace. I agree. Right now, if I have four planes, all I know is that there are points where they may all intersect at a particular point or they may intersect at multiple points, and I can still agree to this point that okay, if they agree at multiple points, then yeah, they form a subspace of a sort. But yeah, can you continue? So
No, that's what. See, even if they intersected at one point, right?
huh.
It doesn't look like a intersection of point. When we see when we check that or when we look at that with a 3D view or four view space,
Huh.
it doesn't look like a point of intersection or a line forming based on their intersection. It just looks like a subspace. Let us suppose four equations when we plot it on the plane, right, or on the graph. What it does is it shows us from one angle. It shows us the partial space of that total graph.
No, but if you like, for example, I'll plot an equation here, okay, and that is say 3x, okay, minus 4y and 3x minus 4y plus z equals 9. Huh. So all of them are intersecting at the same point. Can you see? This gray one is not a plane. Okay, gray one is just showing the x versus y axis. Okay, these are the colored ones. Look at the colored ones. I'll just color this plane also. Something, I don't know, purple maybe. Okay. See, all of them are intersecting at a point. It can always happen, but it need not always happen.
Yeah, as we increase, the chance of intersection is very less. It comes down, right?
as
we increase the
we
equation.
increase, the chance of intersection comes down, but again the only way of increasing our chance of intersection is by increasing the number of planes. You get it, no? I agree that as you increase, the chances of intersection is very slim, but it still increases. Okay, the chances still increase. Now, the point that I was trying to make is now, okay, that what happens if I add two of these equations? Okay, so that's what this equation 4 actually represents. I'm adding equation 1 and equation 2 and getting this equation 4. Notice how 2x plus x equals 3x minus y minus 3y equals minus 4y and 3z minus 2z equals z. Okay, and 9 plus 0 is 9. This is exactly the purple plane here. So what happens when you add? Okay, what happens when you add two equations? Notice how it is a different plane. It looks like a different plane. It looks like a totally different plane. It looks like a slightly rotated blue, and it also looks like a slightly rotated red. Okay, but it looks completely different from green. Okay, but although it rotates, it will always respect rotation about this particular point of intersection. Okay, look at this geometric view. No matter if you add these equations, if you subtract these equations, okay, or multiply even, okay, multiply and add, say, it does not matter. It will always pass through this point of intersection if there is a point of intersection. Okay, let's even remove this blue one. Okay, let's remove the green one. Okay, equation 3, and just look at this one, the red and the blue. Okay, they are not intersecting on a single point, mind you. This was the point where it was intersecting before, right? They are now intersecting on an entire line. So they are intersecting in infinitely many points, or this system has infinitely many solutions. Now, if I did the same that I did before, that is, I added equation 1 and equation 2. I added the equations for the blue line and the red line, blue plane and the red plane. I get this plane, and notice this. It is still intersecting through this entire infinitely many solutions. That is, it is intersecting with that line. It is, in other terms, it is still rotating about the intersection. So this is an important observation, that when you add, subtract, multiply equations and so on, the point of intersection is always respected by even the new line. And this is actually the heart of Gaussian elimination. Okay, and now we get to Gaussian elimination. I hope everything is clear, right? Right? Okay, good. Okay, I hope it's clear for the others also, right? Agni, Satindra. Okay, now I'll present from here. Okay. Okay. Now let's do the same equation but with Gaussian elimination. Okay. See, let's copy this. Great. Okay. One moment. I'll just switch on the AC. Okay. Now, I hope. Okay, great. So now, let's look at Gaussian elimination. Now, this is what Goel was suggesting before. Okay, when I told you guys to try it with substitution, y plus 3z equals 9, x minus 3y minus 2z equals 0, 3x plus 2y minus z equals minus 1. Okay. Now, this is what Goel was suggesting. Goel said that multiply equation 2, this one, this is 3. by 2. This is what he was suggesting. And I got this 2x minus 6y minus 4z equals 0. And then he said, now subtract this from 1. And then you'll get, but then I stopped him. I told him you're getting into elimination, not substitution. Okay. So this, but this is still valid. We've done it in high school. Okay. And what did we call it? We call it the elimination technique, right? And in the lectures also we studied Gaussian elimination. Right. Gaussian elimination is nothing fancier than elimination. I mean, of course, it's an important contribution. Okay, it's a very huge contribution, but it's still the one we studied in high school. The subtracting, multiplying, and so on. It's still Gaussian elimination. The only difference is that we are actually interpreting it as a matrix. We are interpreting it in terms of row additions, row subtractions, and so on. So we are looking at it in terms of row operations, and that's the only difference. So what we do in Gaussian elimination is we write what is called the augmented matrix. Okay. So if we want to write it in terms of AX equals B, we write this as 2 minus 1, 3, 1 minus 3 minus 2, 3, 2 minus 1, and 9, 0, and then this is the A matrix, which is also called the coefficient matrix, and then we have this vector, okay, which is the unknown matrix vector, and then which is equal to B. B is your output. This is how we interpret it, right? The augmented matrix is just A slash B, okay, which means just you add this B as a column to A, and then you write the coefficient matrix 2 minus 1, 3, 1, okay, 1 minus 3 minus 2, 3, 2 minus 1. Oh, and then you add another column, okay, and that is 9, 0, 1 minus 1. We add this line, but this line is nothing special. It just means that, okay, this is a new column, okay. This is what you have now. You get a 3 cross 4 matrix. Okay. Now what do? You just apply row operations, and these row operations are, what they do is nothing more than the high school technique we did. Okay. Under the covers. Okay. So what do? What you want to do is you want to eliminate variables as you. That's what you are doing, right? You by doing this, you subtract from 1, you multiply, and so on. What you are doing is you are trying to eliminate as many unknowns as possible. Okay, and this is the same thing that you are doing here. Notice that this column represents X, this column represents Y, and this column represents Z. Okay, because internally what is it saying? 2x minus 1y plus minus 1y plus 3z equals 9. That's what is happening, right? And if it so happens that you render this to 0, this to 0, it just means minus z is equal to minus 1 or something like that. So that is what you want to achieve. You want to achieve what is called the row echelon form. Okay, which looks something like this. You have a 1, okay, and something here, and you have a 0 here and something here, and you have 0, 0 here and something here. Okay, this is called the row echelon form of a matrix. It need not be an augmented matrix like here. It could be any random matrix. Okay, it could be any dimension of sorts, but it needs to have this property that on the first row, okay, the first and on the first row, the column, the first entry should be a 1 and everything below it 0. On the second row, Okay, the second item should be 1. Everything above it can be anything. Okay, the star represent it could be anything, but everything below should be 0. This is what you want to achieve, and let's work towards that. Okay, let's do that. 2 minus, okay, that's what you have, right? So now you can apply what are called row operations. Okay, immediately what you can do is I can do in R3 I do R3 minus 3 times R2. Okay, and so you have, when you do this, you get 2 minus 1, 3, 9, 1 minus 3. The remaining columns are unchanged, and R3 minus 3 times R2, which is 3 minus 3 is 0, because remember I want to achieve this configuration, so I want to set this to 0. Okay, and yeah, and 2 minus of 3 times 3, so that will be 2 minus of 3 times, that is 2 plus 9, which is 11. Okay, and minus 1 minus of 2 times 3, which is 6. Okay, so 6 minus 1 is 5. Okay, and then I need to apply it for this also. Okay, and minus 1 minus minus 1 minus 3 times 0 is minus 1. I did this. Okay, but what is happening under the covers? Under the covers I'm simply doing equation 3 minus 3 times equation 1, equation 2. This is what is actually happening, because notice that you are subtracting the coefficients also.
Seems the
element wise
should be 0, 11, 5 and plus 1.
Yeah, what you're saying?
The last row.
Yeah,
The last row.
last row. Is there a mistake?
0, 11, 5 plus 1.
Is it plus 1?
Yeah, minus 3 and minus 1.
Oh, okay. Wait. Sorry. 0, 11, then 5 is incorrect, you said? You mean?
5 is correct. 5 is correct.
5 is correct.
And for the augmented value, for the last row, it's minus 3 into minus 1.
Minus 3 into minus 1. No. So I'm doing R3 minus 3 times R2.
R2.
Yeah,
right.
R2. Oh, okay. Yeah. It's R2. Okay. And so what you are below, actually under the covers, what you are doing is you are just simply subtracting 3 times equation 2 from equation 3, because this is actually equation 3 only. I mean, this is actually equation 3, right? You're saying 3x plus 2y minus z is equal to minus 1, and then subtract 3 times R2 from it, and you are just respecting the order. Okay.
So what is the meaning of this modified third row now? Does this mean that the 11y plus 5z is equal to minus 1?
Exactly. 11y plus 5z equals minus 1. That is what is happening under the covers.
So then what is the genesis, or I mean the intuition behind these row operations, that even if you perform these operations?
Yeah. Exactly. That's what we are trying to do. Now what we are trying to do is we are trying to come up with planes. Okay. We are trying to come up with planes which are actually simpler to describe by reducing it to a line. Okay, what do I mean by that? Okay, so what do I mean by that is, you saw that there were several planes. No, you saw that there are several planes. When I say 11y plus 5z minus equals minus 1, is this a plane or is this a line?
This is a line.
Okay, this is a line in 2 dimensions.
Yes.
But it is a plane in 3. It is still a plane in 3 dimensions, because I can always put a 0x here.
At the most, this is a plane, but then this could be the projected plane along certain line.
Right. It is a 0x, but it is still a special plane which we can interpret as a line easily. It does not have a depth component. It is not rotated at a particular angle with respect to the depth. Okay. So I want to come up with such a simple plane which is almost a line. If you see it with 2D, okay, I mean from one of the x, okay, so if I see it from one of the angles x, y, z, I will see a single line. This may not be true for every plane, mind you. It may be that from a particular angle I may see every plane as a line. I agree, but I want to see it as a line from either the x axis, either the y axis, or the z axis when I see it through it. And that is exactly what happens with this. And this is actually what we want to come up with. We want to reduce the dimensions. I have reduced the dimension here. And then I want to reduce the dimension further to a single dimension and get a point. And that point is exactly some z, no? The value of z.
Correct.
Okay,
correct.
that is what is happening geometrically. Okay. So yeah, that is what is happening geometrically. But algebraically, you can see that on adding, subtracting, nothing changes in equations. And you also saw it geometrically that on adding planes, subtracting planes, you get planes, but the roots are the intersections are still the same. Okay. Now I got this. Now what do I want to do? Let's say I want to make this 0. Okay. It's up to you. Let's say I try to make this. Okay, that's easier. Okay. I do R2 in R2. I do R2 minus 2 times R1. Okay. So let's do that. 2 minus 1, 3, 9, and 0 minus 3 plus 2 is minus 1, minus 2 plus minus 2 minus 6 is minus 8, and 10 minus 18 is minus 8. Oh, there's something wrong here. Is it? Is this correct?
0 minus 18. 0 minus 18.
0
minus 18. Minus 18.
Okay, this is minus 18, you mean?
No. That is correct. 0
Okay.
minus 1 minus 8, then minus 18 you will get.
Okay, sorry. Oh, sorry, okay, this is not 10. This is 0. Okay, yeah. This is minus 18. Okay?
Yes.
Great, thank you, Satinder. Okay. Then you have 0, then you have 11, then 5 here, then minus 1. Okay, great. Okay, I'm getting closer and closer to the row echelon form. Okay. And this is what I have now. Now, what do I want to do? I want to finally convert this to a 0. How do I do that? I'll just do R2, R3. In R3, I'll do R3 minus plus 11 R2. This will achieve it, right? Because what I will get is 0, minus 1, minus 8, minus 18. What I'll get is 11 plus 11 times minus 1, which is 0. And here I'll get what? 5 plus minus 88. No? Minus 88, and which is what? Minus 83, right? Yeah, strange number. Let's hope this is correct. So then what do I have? Then I have minus 1 plus, which will be minus now because there is 18 there. 88 times 11. Oh, sorry, 18 times 11.
Minus 198. 199. Minus 199 you'll get, I think so.
Minus 199.
1.
Okay, this is correct, no? Okay. Minus 199. Is it correct? I hope this is correct. But then you will get Z value.
This is correct.
Okay, so far it's correct, I hope. Yeah, okay. Okay, so great. Now what I want to do is I want to make this into 1. Okay, I can actually immediately do one thing. I can immediately say that since this is x, this is y, this is z, this is uh, uh, and this is minus 199, I can always say minus 83 z equals minus 199. Cancel this off. What will I get? 199 by 83. Is this even divisible? No. This isn't. You'll get a decimal, right? You'll get fraction, no? Then I think I made a mistake somewhere.
Is this 83 or 63?
Okay, 5. Did I make a mistake? Should I get 83 there?
53.
5 plus minus 88. It will be minus 83, that's correct.
Yes, the value would be in fraction actually, and which will make other calculations difficult. But
No. Because see, I'm trying the same equation. No, by elimination we got
yeah.
this. No, what did we get by elimination? Some one. This
One-
1 minus 1 2. I should be getting 2 there.
Then there is some mistake.
Yeah. So there is some mistake done. Maybe I wrote it wrong. 2 minus 1 3 9. Yeah. 1 minus 3 minus 2 0. That's correct. 3 2 minus 1 minus 1. No? Okay, this is correct. Now I want to do R3 minus R3 times.
Is it that the decimal values cannot be plotted?
No, it's not that. It's not that. It could be decimal values, but the same set of equations before using earlier when we used substitution, we got this. No, z equals 2.
Okay.
We should be getting z equals 2, but we are getting z equals to some fractional
Okay.
time, which is
Okay.
so. Yeah, that means something is incorrect. So okay, let's do some error correction. So R3 minus 3 times R2, so that will be okay, this is 0, that is correct. So 2 plus 3 times 3, right? 2 plus 3 times 3, which is 11, this is correct. And minus 1 plus 2 times 3 is 5, this is correct. No? This is minus into minus plus 2 times 3 is 6. Okay, good. And finally this one, minus 1 minus 3 times 0 is minus 1. Okay, this is correct. Now maybe there's a mistake here. Let's see. R2, in R2 I'm doing R2 minus 2R1. Okay, so okay, this is 0 minus 3 plus 2 is minus 1.
This value won't be 0 if R2 is R2 minus 2R1. So 2R1 will become what? 4. So 1.
Okay. Good point. It should be 1 by 2R1. Thank you.
Yes, it's okay.
Now it will be 0. Okay, this is the incorrect thing. Okay, so minus 3 plus 1 by 2 will be 3 minus half is 5 by 2, right? Minus 5 by 2. And then I have minus 2 minus 3 by 2, right?
Minus 7 by 2.
Minus 7 by 2. Good.
And then in the right hand side, 9 by 2.
0, 9. Minus 9 by 2. Right? Minus 9 by 2. No. Okay. Yeah. Sorry for the inconsistency. Okay, great. Now, finally, I need to do something about the. So I'll do R3 minus 11, okay, plus 11 R1, okay, and R3. Then I'll get 2 minus 1, 3, 9, 0 minus 5 by 2, minus 7 by 2, minus 9 by 2. Okay. So here I'll get 0. Okay. No, it's better I don't do R3 and R1 because I'll lose that 0. I'll do, okay, this will get complicated, but still let's try. Okay, that is R3, I'll put R3.
Sir, can we divide by 2 by 5 R2, then it comes out with 1, then 11 by 2 we can by 11 we can do. Second row, can we divide throughout by 2 by 5?
You can do that. Yeah, let's do that. Okay. Yeah. So R2 will do R2 divided by 2 by 5. Or you'll multiply by 2 by 5. That's what you mean, no?
Yes, sir.
Yeah.
2 by 5.
2 by 5 times R2. Yes, good. That will simplify it. So if you do it, then it'll cancel out a lot of things. Good. You'll get a minus 1 here. You will get minus 7 by 5. Oh, no. 2 by 5. Yeah, minus 7 by 5. Oh, okay. Still we are getting some fractions, but that's okay. Good. Yeah. And here we'll get minus 9 by 5. Okay, 0, 11, 5, minus 1. Okay. But at least it helped in getting this one. Yeah. Now let's do R3. In R3, what I'll do is R3 plus 11 R2. Okay. Then 2 minus 1, 3, 9. 0 minus 1, minus 7 by 5, minus 9 by 5. And I'll do 0 and 11 minus 11 times minus 1 is 0. And now I'll do 5 minus of 5 plus, which is plus times minus 11 times 7 by 5, which is 77 by 5. Okay, which will come to 25 minus 77 by 5. Okay, 25 minus 77 is something like 52. Is that correct? Minus 52 by 5. Okay.
Yes, sir. Correct.
Okay, good. Minus 52 by 5. And finally, you have minus 1 minus 99 by 5, which is minus 5 minus 99 by 5, which is equal to 104. Minus 10455. Yes, now it's correct. Because this is twice this. No? So if you actually continue Gaussian elimination, you need to bring this to 1. Okay. But we can do that also. Now what I'll do is I'll divide this expression by I'll multiply this expression by 5 times minus 2. Okay. R3
directly it is coming out to be 2 only. If you equate, then directly it is coming out.
That's right, Satinder. That's what I was saying. This is equivalent to saying 52 minus 52 7z equals minus 104 by 5. But if you try to respect the algorithm of Gaussian elimination, you need to set everything to 1 1 1. Okay. Okay, but yeah, I still agree with you. So what I'll do is R3, I'll set it to 5 minus 5 by 52 times R3, and then what I'll get is 2 minus 1, 3, 9, 0 minus 1, minus 7 by 5, minus 9 by 5, and 0, 0, and 1, and 2. Right? This is what I got. Okay. Now what I'll do is I'll again multiply the second one, R2, by R2 minus 1 times R2. Okay. and make it 2, minus 1, 3, 9, 0, 1, 7 by 5, 9 by 5, and 0, 0, 1, 2. Okay. Now finally, to get it to row echelon form, I'll simply divide by 2, the first one by 2. Are 1. Okay. So I'll get 1 minus 1 by 2, 3 by 2, 9 by 2. Okay. 0, 1, 7 by 5, 9 by 5, 0, 0, 1, 2. Okay. Now, this is what I have. At this point, I can just say that z equals, 1z equals 2, and then 2x, and this guy, okay, I'll write it in order. Okay, I'll write it in order, that is x minus y by 2 plus 3 by 2 equals 9 by 2, y plus 7 by 5 equals 9 by 5, and z equals 2. Okay, 7 by 5 z. Now what I'll do is I'll plug this guy here.
3z by 2 in the first equation.
Sorry, yeah, thank you. Okay, I'll plug this guy here, and then I'll get the value of y equals minus 1, and then I'll get x equals 1. Okay, I think that's what we are supposed to get. Yeah. Okay. Now, okay, great. So this is okay. It was a rather long calculation, but that's what I got. I got the same thing, basically minus 1, 2, that I got from substitution. Now, there is an offshoot technique called Gauss-Jordan elimination. Okay, just the one we saw was Gaussian elimination. It is same as the elimination method.
I have one query here.
Yeah.
So when we do say 5R2, so R2 is a plane, and then 5R2 would be what?
Could you repeat that? R2?
So R2, so the second row will give us a plane. I mean, in this R2, so
for example, here you mean?
Yeah, here. So in this augmented matrix notation, how to interpret, say, the second row? Second row could be, I mean, maybe viewed as equation of a plane written in a different order. And say if I multiply the second row by 5, so it corresponds to what? The same plane, but then what?
Exactly. So
same plane.
Yeah, it will still be the same plane. So scalar multiple of a equation of a plane will still represent the same plane. It's like saying if you have a line, let's say x equals y, okay, and what does the line look like? This, okay. At 1 it will be 1, at 2 it will be 2, and so on. If I do 2x equals 2y,
yes,
it is still the same
line. So now when we perform, say, R2 minus 5R1, say when I assign the updated value of R1 as R2 minus 5R1, say R2 is equal to R2 minus 5R1.
R2 equals R2 minus 5R1. Okay.
So what does this mean? That, I mean, what will I get? See, I'm second.
Exactly.
Yeah.
So in the beginning, do 5R1 first. This 5R will still represent the same plane.
Yes.
And so you are just subtracting R2 minus the plane of R1, which you still know that the solutions will not change.
So, but then this plane minus plane. I mean, what's the meaning of this plane minus plane?
Okay. Yeah, I mean that is it's easier to imagine in terms of vectors. Okay, but I'll just tell you that it is still a form of rotation along the axis of intersection. Okay, as you saw it that time.
Yes, so while explaining the things, you mentioned something that the point will get respected, whatever operation.
Exactly.
That respect point was not clear to me, actually.
So what I mean is, if two planes intersect, okay. Yeah, sir.
Sir, I was just telling we have studied in the junior classes that okay, if you get P1 plus K times of P2, it represents the family of the plane which passes through the common point of the intersection.
That's right.
I think I think it represents same idea. It is like P1 plus P2 or P1 plus K times of P2. It represents the that plane which actually passes through the same. Means it is a family of the all the planes which is passing through the common line. I think.
That is true. That is true, Satinder. So that's what I meant. But if you say it passes through the common line, how does it look like? Right.
Yeah.
So Satinder, that's right. So if I have one plane P1, okay, and I do K times P2, or let's say I remove the K also. Let's for simplicity's sake, okay. Because I know that for any P2, the plane represented by K times P2 is still same, right? That's what we were saying, that the line, it does not matter if I do 2x equals 2y or 3x equals 3y, it represents the same line. So let's for simplicity say that P1 plus P2, okay? It is the family of planes that passes through that passes through the intersection of P1 and P2, okay? So that's what you said, no? P1 and P2, there is an intersection.
Yes,
And,
means now this represents a new plane which passes through the common line. Means what you have shown just now in the I think 3D picture you have just now shown also. When you are adding, so you are getting the new plane passing through the intersection. Just now you have shown also.
Exactly. But yeah, that's right. And how does this? When you say that all these planes pass through the same intersection. So, for example,
Yes.
let's say this is P1, and let's say this is P2. Okay. And I do a P1 plus P2. Okay. So that will be P1 plus 1 times P2. Hmm. And what will that look like? Well, it will pass through the same point. It needs to pass through the same point of intersection, which is a line.
Yes.
You get it, no? Now, it does not matter whether I do plus 2p2 also, because 2p2 anyway represents the same plane. Okay.
What about minus 2?
Now that's another good question. What about minus p2? Okay. So how it behaves when you do a minus, I think needs some kind of investigation. But let's say it appears here. Okay. It appears here, but it still needs to still pass through the same point. And I do, let's say I do some crazy things like P1 plus P2 plus P1, something like this. Okay. Here I got a new plane again. Right. I got this plane. No. And I added it to the original plane. It still needs to pass through the same intersection. Right.
Right.
And so let's say this is the plane. Right. And then I keep doing different combinations, okay, of this, which are actually called linear combinations, which you'll find out in the next next session, okay, and so on. And you keep doing this. What do you see? You see that it's the same plane, but it is getting rotated, right? It is the same plane. This axis wise, it's the same plane. I mean, sorry. This side wise, it's the same plane. This side wise, it's the same plane. It's not rotating there. It's only rotating with respect to this axis.
Yes.
Right. And so this is what addition of planes represent. It represents rotation.
Oh, I see. And this intersection line would always be respected, whichever operation.
Exactly. So since this intersection line is always respected, you can always add equations. You can always subtract equations. Okay, you can do a scalar multiple, of course, but you can even add to a scalar multiple of another plane, and still it will rotate across the same intersection. And what is this intersection? This is the solution to the set of system of equations. So even if you add, subtract, whatever, it always rotates around the same axis, which means it will always intersect at that particular axis.
Yes.
And that means that the solution to the system of equations will never change if you add or subtract.
Clear to me. Thanks.
Okay. Yeah, Satinder, is that right?
Yes, sir. Yes, sir.
Okay. Yeah, Kishore.
Yeah, see, when we talk about the minus values, right, just before Goel has raised. So, see, when we put into in terms of XY plane, right, XY coordinates. So what it does is it comes to the minus valued quadrant. It's the same thing when we compare it to the n space. I mean, like n equations, n type of equation.
Yeah, yeah. Even if you do it on an XY plane and you do not, you add a third axis to it, you just do an XY, it will still be this. If you add, you can test it for yourself, or I can show it in the 3D plotter if you want to see. If you have this a line, oops, where is it? Okay, if you have the line 1, okay, let's say you have your x-axis and y-axis, okay, and you have this, okay, and then you have, let's say, a separate line, okay, which is the second line. This is your line 1 and this is your line 2, and they intersect at the same point. If you add these two lines, L1 plus L2, it could be something like this. It is as if I was rotating L1 along this axis, along this point, around this point. Or it is also interpreted, can be interpreted as I'm rotating L2 along this point in either direction. It does not matter. And this is one of the reasons why we were talking about this in the lectures. We were talking about these homogeneous equations, right? Homogeneous system of equations is of the form Ax equals 0. Okay, which means a trivial solution is always that x I set it to 0, so Ax will always be equal to 0. So it is always looking like this. Okay, it is always looking, all the lines look like this. Yeah.
Sir, can be like we have this just now what question we have solved. Three equation of the plane is there. So if we can do some transformation like it becomes homogeneous, could it be possible equations can be reducible to homogeneous by shift of origin?
That's a very nice point. Can you shift the origin and make it homogeneous? That is, it's a very nice trick in mathematics. You can't, of course, you can't literally shift it there, but you can pretend that the origin is somewhere else.
What I'm thinking, like suppose if unique solution is there, first of all, anyhow we can come to know, okay, this system will have unique solution. So if because homogeneous have only two things, homogeneous equation will be always consistent. So we can come to know. So if we'll do shift of origin, so by that only we can come to know, because shift of origin is possible only if it is consistent. Otherwise, I think shift of origin it won't come.
Right. That's a exactly.
So if any technique will be there or any method will be there by which it will be reducible to homogeneous, so it will be, I think, easy for a student to calculate this.
Exactly. It's not always possible. It's not always possible, but there is one underlying problem with it. Okay. That is where do you want to shift the origin? You want to shift the origin to the solution of the points, right?
Yeah.
But what are you trying to find? You're trying to find the solution. So there's a sort of circularity here. You get it? So homogeneous equations, okay, homogeneous equations look like this. No, they pass through the origin. And what you are trying to do is you are trying to take a non-homogeneous equation and then bring it to homogeneous and try to solve it easily.
Okay, means it will be never possible.
But
this will be not possible.
No, I won't say. It is not possible. Okay, it is. It has a circularity
because
to it, but this is an important.
I think it is just hit and trial method. Then it will be.
You never know where the equations will meet, because if you know where the equations will meet, then you cannot solve it. No, I mean, you cannot solve. You've already solved it. No.
What I'm thinking, like two equations will be reduced to like equal to 0. Two equations can be made homogeneous out of 3. So 2 definitely can be made to 0, I think, by transformation.
That's a good point, that you cannot use this converting to a homogeneous in order to solve the equations, because in order to convert to homogeneous you need to solve the equation, as you can see it, right? But this technique is used to solve it first and do something else with it, compute some other activity. Because whenever you shift it to the origin, things become much more simpler if you want to perform more complex calculations. So there are techniques, of course, that you can actually shift it to the origin, but you need to solve it for it. But for this particular problem, that solving the equations itself, you are shifting it to the origin, that cannot be possible, because in order to do that, you need to know the solution. Okay. Yeah, Kishore?
See, when we say shifting the origin, is it something, see, in normal, 0, 0 is the coordinate where we have the origin, right? It's something when we say we shift, does the coordinates becomes 1, 2 or 1, 0? Is it that's how it becomes?
The coordinates becomes...
I mean, like, see, when we say shifting the origin, see, basically the origin will be at 0 and 0 coordinate, right?
The
0,
origin will be 0, 0 coordinate.
Excuse me, sir.
Yeah.
Just I want to clarify this part. Shifting the origin doesn't mean it will be there. We are looking at some new coordinate system. We are making another. What is our original coordinate system? That will be at the 0, 0. So we are taking some frame of reference at another point, and that we are treating as origin, but it is not actually origin. So that is the concept, I think so.
That means we are changing the coordinates, right?
Yeah. Sir.
So yeah, I'll show you once. Okay, I'll show you. Wait. So I'll show you on the plotter. Okay. Can you see my screen?
Yeah.
Okay. Let me come up with 2 lines. Okay. I don't want to work with planes. I'll come up with 2 lines, and that line will be okay. This is my equation 1. This is x plus 2y. Oh, what am I? Okay, x plus 2. Okay, this is y equals x plus 2. Okay, and I'll add another line to it. X minus y equals 3. Okay, it's 10. Okay, I need to put another here. X minus 2y equals 3. Okay, or let's do x2 x plus 2y equals 1. Is it better? And x plus 3, yeah, good. Okay, now you have this, no? Make it plus. Okay, you have this, no? You can see that it's intersecting here somewhere. No. Now what you can do, who asked it? Satinder. Yeah, right. So Satinder, what you can do is, you can say that, oh, where did it go now? Okay, you can say that this is f, let's call this one g. You can say that I will shift this guy, okay, I'll shift this by 2x, and this guy also by 2x. You see that I've shifted it, right? I've shifted it more towards the x-axis, but the lines are still the same. You can see that only their intersections are moving. Okay, again I'll visualize this by saying that I'll shift this by 2.5, I'm shifting by 2.5. You see that the lines, the orientation is still the same. I'm shifting it. You see that? And I say I need to now increase it a little bit more. 3. I want to bring it to the origin. Okay. And okay, even 3 is not okay. Yeah, let's try 3. Okay, even 3 is not good enough. Let's say I try 5. Okay, now I'm very close to the origin. X axis wise, let's say I put 8. Okay. Okay, now I'm very close to the origin. Let's say I'm okay. Now I what do? I want to bring it down. I want to reduce it. So I do it this 2y. I multiply it with minus 2y, and here too I multiply it with minus 2y. Okay, see, I've shifted it down. It's too down, too much down. I'll bring it a bit above. Okay, as you can see, I'm shifting those lines, but okay, I'll bring this minus.
Sir, pardon, sir. Sir, like what I was saying, like just now for 2D, we have the equation. First equation we have y equal to x plus 2.
Huh.
So what I can visualize, because it is 2D, so it is very easy to just find any two solutions.
Yeah, it's easy. That's right.
Any two solutions. So if I'm taking x equal to 1, so y I'll get 3. 1,
That's
3
right.
coordinates.
That's
And
right.
now what I'll do, I'll take now x equal to 2, so y I'll get as I think 4.
Right.
Now, so if I want this line to pass through the origin, so I'll shift one of the coordinate. One of the coordinate, if I'll now make it 0, like 1, 3, 1, comma 3 is there. So this I have to make as 0. So I have to subtract 1 means 0, and from both. So this comes out to be 0, 2, and next will be like in second equation also I have to subtract that part.
But how do you make sure that they still intersect?
So because now the same line, because if I do the shift of origin, so just now what will happen, just the coordinates will shift. So when I'll get the point of intersection, so how much I have shifted, that much further I'll add it back.
Exactly.
So
exactly.
I can
So that is what you would do to shift the or to the origin. Exactly. Right.
Yes, sir. Yes, sir.
But what I'm trying to say is, in order to do that, what did you do? You solved it.
Because it is 2D, so we know how that from the 2 points how to get the equation. So it will be easy. But for 3D, I have to get 3 different points. Then I have to find the equation of plane, because our target is not of 3D. It may be of many dimensions. So that will be impossible for, I think, that approach. I think.
Yeah. It's circular. Exactly. In order to solve it, you are saying you'll shift it to origin. But in order to shift it to origin, you need to solve it.
Yes, sir. Yes, sir.
So you see that, but this technique is actually useful. It's not like it's only for. It's not useless at all. It's useful to do other kinds of computation, but not to solve it. Because in order to solve it, you need to. In order to do this, you need to solve it. Okay.
Yes, sir. Yes, sir.
Okay. So I'll just quickly talk about. Okay, everything is clear, right? I think. I hope. I'll stop screen sharing here. Okay, wait. So now, okay, that is done. Now, what we are talking about is called Gauss-Jordan elimination. Okay. Now, Gauss-Jordan, you notice that in the row echelon form. Okay, row echelon form. It was you wanted to achieve this. And then maybe the B1, B2, B3. And of course, there need not be B1, B2, B3. Row echelon form is true for any matrix. Okay, you can say that this is a row echelon form matrix. Okay, but you wanted something like this. But Gauss-Jordan method just says that you just use row operations continuously. Don't stop at the row echelon form. Okay, use Gauss-Jordan, use row operations and continue until you get something like this. And if you have a square matrix, then it'll look like this. It'll look like an identity matrix. Okay, almost. Yeah. Okay. Now,
So the only the when in whichever column one repeats, right? So the rest of the element should be 0, 0.
exactly. So in Gauss-Jordan form, the ith row should have ith column. Sorry. Oh, ith column should have ith element as 1, all else as 0. So first row has the first column has the first element as 1, everything else 0, and so on. Okay, starting from going from left to right. Yeah, well.
What about the fourth column?
What about the fourth column? Fourth column need not be anything. The fourth column need not follow that. The fourth column could be anything.
Yes.
Okay. So I'll come to the advantage of row echelon form, but first let's apply row echelon form. Let's not stop at this point when we did for Gaussian elimination. Okay. Let's continue here where we left off. Or let me do a new page and continue here. Okay. Let's do here. And so how do we eliminate the other rows? Okay, what we can do is in R1 I can do R1 minus 1 by plus 1 by 2 times R2, right? That will make this 0. 1, 0, and then I do 3 by 2 minus 1 by 2 times 7 by 5, which is equal to 7 by 10, 3 by 2 minus 7 by 10, which is equal to 30 minus 14 by 20, which is equal to 16 by 20, which is equal to 4 by 5.
This is addition, not subtraction. 3 by 2 plus 7 by 10.
Oh, sorry, yeah. So this will be plus, and so this will be 44 by 20, which is 22 by 10, which is 11 by 5. Oh, yeah, 11 by 5. And then I do the same thing with 9 by 2. 9 by 2 plus 9 by 10, which is 1 by 2 plus 1 by 10, which is 20, 10 plus 2, 9 by 20 times 12 by 20. 9 times 12 by 20.
Something is wrong here. This should have been 54 by 10, final answer.
4 by 10?
54 by 10.
54 by 10. Oh, okay, because 9 by 12 by 10, 6, 9, yeah, 54, that's correct, yeah. Yeah, okay. Now I am closer to Gauss-Jordan. Okay, now I have some part remaining, so what I'll do is I'll remove this also. Okay, I need to, but if I need to remove this, I'll need to subtract this guy.
11 by 7. So R1 is equal to R1 minus 11 by 7 R2.
You mean R1 equals to R1?
R1 minus 11 by 7 R2.
That's correct.
Sir, R3 will be subtracted. R3 will be subtracted.
Yeah, we can do R3. 11 by not 7, 11 by 5 will be enough, no? R3. Yeah.
Yes, that is also.
So I'll do 1, 0, this will be 0, and 54 by 10 minus 22 by 5. Okay. Which is 10, 54 minus 5, 2 is 10, 44, which is 10 by 10. Okay. Which I'll get as 1. No? And then 0, 1, 7 by 5, 9 by 5, 0, 0, 1, 2. And finally, what do? I'll do R2, I'll put R2 minus 7 by 5 R3. And then I'll get 1, 0, 0, 1, 0, 1, 7 by 5 minus 7 by 5, 0, 9 by 5 minus 2 times 7 by 5. So 14 by 5, which is equal to 5
by
9.
5.
Yeah, minus 1. Minus 1. Great. So this is what I get. And this can be interpreted as direct, since this is x, this is y, this is z, we can say x equals 1, y equals minus 1, and z equals 2. Now, this is just Gauss-Jordan technique, is just keep doing the row operations until you get this row echelon form. Okay. Now, you might ask, like, why use this? We were fine with Gauss technique, right? It's just a matter of simplification. Further simplification. And why is this even named as a different technique? Because this is almost Gaussian elimination. I agree that this is almost Gaussian elimination. An important fact about this, which you will learn in the coming lectures, is a fact about rank. Okay, a fact about rank. Rank is a very important concept. Okay, it teaches you about whether a system of equations can be solved or not. Okay, whether there is a unique solution, whether there are infinite solution. Okay, and whether there is no solution, of course. But an additional usefulness of rank, okay, comes in next week again in terms of vector spaces. Okay, in terms of vectors, when you interpret it in terms of vectors, what kind of spaces can you build? Okay, there are these concepts of span and so on. It becomes very interesting and beautiful later on. Okay, for now, bear with me that rank is an important concept. Okay, and for example, if you had, so what is rank? Okay, what is rank? Okay. Let's say on getting the row echelon form, instead of getting 1 0 0 0 1 0 0 0 1, you got something like 0 0 0. Okay, you got something like this. Then what would you interpret it as? X equals 1, y equals minus 1, z equals, could be anything. Right, because what I'm getting here is 0x plus 0y plus 0z equals 2. No.
So probably out of the three, the one plane might be representing the same information and nothing new. If we after making lots of simplification, if we come up with a situation where in the last row comprises of all zeros, then this would mean that no new information is added by the third plane.
Exactly. So what does that mean if no new information is added? It means that there are infinitely many solutions.
Yes.
No? Infinite solutions. Why infinite solutions? I can take z equals 1, 2, 3, minus 1, 32, whatever. I can take whatever, and there are infinitely many combinations that I can come up with. And now, what is rank? Okay, what is pivot? These elements, the leading ones, okay, these are called pivots. In the matrix, they are called pivots. Okay, and what is rank? Is equal to number of pivots. Okay, and this guy is a non-pivot. But notice in here, all three of them were pivot. So what is the rank of this matrix? Number of pivots, which is 3.
2.
And what is the rank here?
2.
2. Good. So what does it mean when? So it simply means that when rank is equal to the number of variables n, or the dimension of the matrix, whatever you can say, rank is equal to number of variables n, that is number of variables, then system has a unique solution. Okay, and if you say rank is less than n, okay, then system has infinitely many solutions. Okay, and well, you might ask, what about no solution case? Well, no solution case is an inconsistency case. Okay, you will get something like when there is no solution, you will get something like 0, 1, 1, 0 is equal to 1, and 0, 1, 1, 0 is equal to 2, something like that. This is a no solution case, but rank is very useful in checking whether there is a solution or not. Okay, and you'll see that next time.
Yeah. See, when rank is equal to n, can we say the equations are inhomogeneous?
No, you cannot.
Okay.
Okay, because if you it depends on what you if you say that the equations are homogeneous, okay, I'll give you 2 reasons. Okay, first reason is this example itself is not homogeneous, because the equations are x equals, okay, the this is the final solution, and this is not homogeneous. Okay, because it's not of the form ax equals 0. Okay, another reason I give you is, if the equations were homogeneous, already you say that already it means that either the system has a unique solution which is equal to 0, or the system may have infinitely many solutions. But this is not true for all matrices, right, with rank equal to n. For example, this is rank equal to n, but its solution is neither infinite nor is it trivial. By trivial, I mean x equals 0, y equals 0, z equals 0. So this is an example of a non-homogeneous equation with rank equal to n. Okay. So, but what will homogeneous look like? Okay, what will homogeneous rank equation will look like? Homogeneous system look like? It will look like this. Okay, on the right hand side, everything is 0. X equals 0, y equals 0, z equals 0. So this is what homogeneous will look like. Great. Now, okay, we have very little time. We have like 9 to 10 minutes. Okay, let's look at the other questions. Okay, and okay, determinant, another important concept. Oh, by the way, we saw Gauss elimination, Gauss Jordan technique, and using inverse we did not see, right? And this is something I want to talk about, but first I just want to quickly talk about determinant. Well, what is determinant? You've already seen in your high school probably that if I have A, B, C, D is a matrix, okay, then the determinant of A is equal to AD minus BC. Okay, and you may also have seen that if A is A, B, C, D, E, F, G, H, I, then the determinant is take A outside and determinant of E, F, H, I. Okay, and this part, and take B out and put a minus sign, B determinant of D, F, G, I, and plus C determinant of D, E, G, H. Okay. Now what then this is how you compute a determinant, and if you say that if I have a matrix which is 4 by 4, how do you compute determinant? Well, then the formula becomes complicated. You need to represent in terms of permutations and so on. You have summation of some monomials, okay, and then you need to do something like I sigma I, and go across all possible sigma permutation. But it's a very difficult formula to state. It finally makes a polynomial, okay, a sum of monomials, but it's a difficult concept. And computationally, determinant is something we still not know whether it can be done efficiently. I mean, it can be done efficiently, but we do not know whether it can be done very efficiently yet. Okay, but so in short, you can always say that determinant computation is not always very simple to do, and but finding inverse is something even slightly more complicated to do. Okay, what is inverse now? If you have a matrix A, okay.
So any geometric intuition of computing the determinant of a matrix then? I heard it is similar to area kind of thing, not sure.
That is true, that is area. See, in any system of any matrix, you can interpret it in two ways. One as a system of equations. This is called the row view. The other view is a bunch of columns, okay, vectors. So this is called column view. Okay. In the vector view, what are vectors? Vectors are just points in space. And you'll see in the coming week that determinant is of the matrix represented is just the area of the parallelogram passing through the points. Okay, so if you have your 3 points as this, then it's the area that area of this particular I mean the points as and then draw a parallelogram with the points. But the row view, okay, is not very clean if you think about it geometrically. Okay, the row view is always as a system of equations. Okay, what is the row view of system of equations? The determinant of A represents whether there are solutions, unique solution or not, or consistency or not, rather, that's a better. So if you ask me with the current knowledge, what can we talk about determinant geometrically, I can only be able to tell you this yet. Okay, in the next week we'll see that there is actually a very nice characterization if you interpret it as vectors. Okay, but if you interpret it as rows, system of equations, this is all that you'll be able to, I'll be able to tell you at least.
Okay, and determinants, for determinants to compute the determinant, is it necessary that the matrix be a square matrix, or can we compute the determinant for any matrix?
It is necessary that it's a square matrix. Yeah, it is. I mean, the formula of a determinant itself is something that requires that it's a square matrix. Yeah. Okay. Yeah. Now, just quickly, I just want to tell you that, okay, but why does determinant judge, okay, the existence of solution? Okay, before that, I just want to quickly say what inverse is. Okay, now what is inverse? What is the multiplicative inverse? Inverse of a natural number. Okay, for example, inverse of 5. Okay, inverse of 5 is that particular thing which you multiply. Multiplicative inverse of 5 is that particular thing which you multiply with 5 on either sides such that you get a 1, which is called the multiplicative identity. Okay, such that you get a 1.
Yes.
So
1 by 5.
1 by 5. And here 1 by 5. Again, and this is the inverse. But I've said of a natural number. No, 1 by 5 is not a natural number. So for natural numbers, multiplicative inverses don't exist. So I need to write it as real number. Okay, for real numbers they exist, or rational numbers they exist.
Yes, that is why people used to say, natural set of the natural numbers does not make a field. Because
yeah. Natural numbers don't make a field. Natural numbers don't make a group. Okay, and that's the reason. But natural numbers do have additive inverses. It depends on what your operation is. That's why. So natural numbers, okay, they don't have additive inverses also. I'm sorry. Integers have additive inverses. What is additive identity? It is 0. You want something that you add to 5 such that you get a 0, which is nothing but minus 5. But note that if I was taking 5 as a natural number, then this is not a natural number. So natural numbers don't even have additive inverses, but as integers they exist. But integers don't have multiplicative inverses. Okay, because 1 by 5 is not an integer. Okay. Anyway, okay, but now what is an inverse of a matrix? Well, inverse of a matrix simply means that on multiplying A with another matrix on either directions, I should be able to get identity, which is I, multiplicative identity. Why is this the multiplicative identity? Because if I multiply additive I on any matrix M on either direction, I'll always get the original. Just like here, no matter what number I multiply with 1, I get the original number. Similarly here, no matter what I add to a number, I'll get the original number. Similarly, identity matrix has this property that no matter what matrix I multiply it with, I get the same matrix here. Okay. Now, now the question is, what is that special matrix that does this? And that is what is called the inverse. Okay. Now, why is inverse interesting? You will see that in the next session in terms of vectors also, but inverse is supposed to undo the operation that the original matrix did. Okay. So I already said that A times A inverse is I. Okay. Now think about this case. AX equals B. Okay. AX equals B is the system of equations. Let me multiply by the inverse by A inverse on both sides of equation. Let me left multiply. Okay, from the left. So I get A inverse times AX equals A inverse times B. Okay. Now this by principle is identity times X equals A inverse B, and you know that identity multiplied with any matrix is always the matrix itself, so X equals A inverse B.
But then inverse can be computed only if the matrix is a square matrix.
Yeah, I'm going. Yeah, exactly. I'm going to come to that. Okay. Now you have X equals A inverse B. Now, and where was I? Oh yeah, okay. So x equals A inverse B. Now, what is x? X is just your unknown. Right? Times 1b, 2b, 3. Okay. So here is a technique to actually solve a system of linear equations. Okay. How do you do that? You compute the inverse. Okay. Now we are already we have a lack of time, so I'll just tell you right away that you saw it in the lectures that inverse is equal to 1 by determinant of A times the what is called the adjoint matrix. Okay, 1 by determinant of A times the adjoint matrix, and computing this adjoint matrix itself is not very easy. Okay, but this is the term of interest, determinant of A. Now notice what happens if determinant of A is 0. Then A inverse will be undefined. No, A inverse will be undefined. So that will mean that this is undefined, this does not exist. So it means that the solution itself does not exist. This means that solution does not exist. Okay, if the determinant. And interestingly, okay, now the question is, then if solution does not exist, when does the solution not exist? When determinant A is equal to 0. Now I ask you, when is determinant of A equals 0? Okay, this is okay. Now determinant of A equals 0 when rank of the matrix A is less than n. Okay, so if you look at the matrix and then A, and you say what is the rank? Well, I'll actually bring it to reduced row echelon form, which the Gauss using Gauss-Jordan, and I get something like 1 0 0 star 0 1 0 star, and I get here 0 0 0 star. Okay, I'll remove the star with some actual numbers 1 3 7. Here we said that the rank is what? 2, because there are only 2 pivot elements. No. Yes. And notice that 2 is less than the number of variables. Okay, number of variables, which means what? Which means that there is no solution. That is what we were saying, right? Sorry, there are, there's no solution or infinitely many solution. That's fine, but the other way to interpret it is find the determinant of this particular matrix. You'll get it to be 0. Okay, and another thing. Okay, another thing is determinant is equal to 0. Now when what? Now when can you find the solution? Okay, if A inverse exists, then you can always find the solution. Okay, wait one moment. X equals A inverse B. So if A inverse exists, then we can always find solution, right? Because it's only a matter of multiplying. You will definitely get a vector of numbers. No, you'll definitely get a matrix containing some numbers. So definitely we can always find the solution. Question is, A inverse does not exist, then we can't. That is the only case when we can't. And when does it not exist? Look at this. A is 1 by determinant of A times the adjoint of A. And this A inverse will not exist only if this determinant is 0. Otherwise, any number you put, you'll always get a matrix finally. right? Any value of determinant which is not 0 will always give you a valid matrix A inverse. So it means that if determinant of A is not equal to 0, then solution exists. Okay, and that is the importance of determinant. Of course, I did not do this question, but please try it on your own. Just compute the determinant of this matrix, and maybe we can discuss it next week. But it's more important to know why determinant is important.
But then calculating, I mean, using this formula seems to be very, very difficult. Like in the areas like machine learning and the deep learning, a matrix of the size, say, million cross millions, is not unusual. So
Right.
then how to compute the A inverse? And machines used to compute, I mean, these values so very quickly. So what is the, I mean, how do machine used to calculate the determinant and the adjoint thing so quickly?
Okay. So to do that, well, I can either use this difficult formula to compute that matrix, or there is another nice thing is that row operations do not change determinant. Okay, row operations do not change determinant, so I can subtract two rows. I can even do one nice thing, which is swap two rows. Okay, but now you'll say that okay, swap was anyway valid in the system during the Gauss elimination thing, right? Because swapping would simply mean I'm just instead of writing equation 1, equation 2, equation 3, I'm writing equation 1, equation 3, equation 2, right? So you could say it's valid, but in the case of determinants, when you swap, the sign will change. If the determinant was originally 5, on swapping, the value of the determinant becomes -5. At the end, it's only a matter of saying plus being minus, minus became plus. Yes, Satinder. Yeah, Satinder.
Excuse me.
Yeah.
Sir, just I want to know, like we have the system equation. So whether it is 2D or 3D or many dimension, whatever it is.
Yeah.
So what right hand we have, like if I'll say like D1, D2, what the result we have? Ax plus by is plus cz equal to d. So what D1, D2, D3 is there? We are considering that as a point for this, means when we are shifting, like when we are doing the transformation. So I think this coordinate we are taking as a point, something like that.
So when you do the row operations, you mean when?
No, that I'm not asking. I'm saying like any equation is there, like written 2x plus 3y equal to 5, suppose. Okay. So this 2x plus 3y equal to 5. So this 5 we are considering as a point. If you are making in a like a matrix form or something, so this 5 we are considering as some point.
Okay. No. So this 5, okay, that's a very philosophical question, but this 5 sort of represents what are the values of x and y that will always let this line become 5. So
I'm getting like one more equation. Let's write below it. Okay. Like we will write x plus 2y equal to 8.
X plus 2y equals 8. Okay.
So now what I'm thinking just now, like. We are transforming this as Ax equal to B matrix, something like Ax equal to B.
Yeah, so, Ax equal to B. Yeah.
So when we are using either Gauss-Jordan method or we are calculating by A inverse, so what I'm getting this as 5 and like 8 is I'm just seeing as a point which has been transformed to the which has been aligned into the A inverse, something like that, which satisfies in this.
No. So 5 and 8 are actually not points. I mean, they are not points in space yet. I mean, if you interpret in column fashion, I was talking about in the next week, then yeah, I agree that 5 and 8 are points. Okay, but if you are interpreting them as planes, equations, lines, then 5 and 8 are not points. They are the value that 2 points, when you add them, you get that 5. Okay. So 5 and 8 itself are not points. But when you apply Gauss-Jordan, I told you, right, if there is an intersection between two planes, when you are doing these row operation column, you are subtracting, adding rows, they are rotating across the same axis. So the line of intersection never changes. So if they are intersecting across this line, this never changes. I'm just rotating the two lines there. So this is what actually happens with row operations, column operations.
And that's
Point-
only what I was that only what I was observing. Like when we are applying the Gauss-Jordan method, so we are getting here identity matrix. So somewhere what we are trying to do, like we are considering this 5 and 8 as some vector. Like I think so.
5 and 8 will be vectors in the you'll see it in the
That
coming
vector
week.
will be- So now, what I think is that vector now A inverse because actually indirectly actually it is multiplied.
Yeah. Okay. Now I get what you are saying.
This 5 and 8 may be transformed to the by A inverse is a transformation type of something.
That
which 5
is
and 8 has
yeah. Now I get what you're saying. You're talking about the column view of it in terms of vectors.
Yeah.
I agree completely.
Yes.
5-8 is the point that the transformation leads to, and if you apply an inverse, it means where you started with.
So exactly we'll get that set of points which satisfies both the equation there.
Exactly. Yeah, exactly.
I think the person who has thought in that way actually has a brilliant idea who has developed this.
Oh yeah, definitely. Yeah. It's the inverse. I didn't want to mention it because I didn't want to spoil the next week's content.
Okay.
Yeah, but
Actually,
yeah.
Sir, can we have in next Tuesday? I think your class is on Tuesday only.
Yeah.
So next Tuesday, can we have this one? Like suppose we'll take one matrix A and try to see like geometrical interpretation of the A inverse. That actually A inverse what it is doing to the this points to that.
Yeah.
Can we have
Next next week it's possible because we are covering that vector content. So
Because,
I can.
just now what we have shown actually it was very interesting. So what I have the confusion last time if it is rotating then what will happen. So today the lecture was very good. Like I enjoyed that part because I got the idea that that thing was there.
Oh, nice. That's nice. I like that you enjoyed it. If you enjoyed this one, then you'll definitely enjoy the coming classes more because the two perspectives that you see of linear algebra is really nice. Also,
Yes.
the thing about computing. Well, you were asking about computing this. No, the determinant.
Yes.
Since you already have a background in complexity, I just want to check this out. Okay, this is NC algorithm for determinant. Okay,
Sure.
check this out in the internet. This shows that actually determinant can be computed very fast in parallel.
Okay.
There are parallel algorithms, right? Okay.
Sure.
Yeah. Okay. Anyway, we came to the end of the session. Okay. I hope you guys enjoyed it. So with this, I will end the talk. Next session will be Tuesday again, 6 p.m. Okay.
Thank you so much.
Okay.
Thank you, sir. Good night, sir.
Okay. Thank
Good
you.
night, sir. Thank you.
Good night. Good night, Satendra. Yeah. Good night, girl.
Yeah, good night. Bye.
Yeah. Okay. Thank you.